Hello everyone, welcome to another video. I'm Shruti Mandaokar. I'm currently a master's in computer science student at Purdue University, Fort Wayne. And today you and me both will be reading this book called Deep Learning with Python by François, and hope we have a good study session of about like 1 hour. We'll be going through the book page by page, and we'll be learning the concepts paragraph by paragraph, trying to like learn it and visualize it so that it goes into our subconscious mind. I'll be also playing a sweet soft background music just to like keep us on track, but hope it will be a productive study session. Let me share my screen. So I have this book open, and this is chapter 12 from Generative Deep Learning by Deep Learning with Python by François. Can show you the cover. This is the book, François Chollet, and let's see where is the chapter page number. I'm gonna start with the last chapter because I think that's the most important one, and then we can go slowly towards the other chapters as well. So let's head to page number 366. I'm right now in my college library, and nobody's here because it's a weekend. I'm hoping that I can make a study session of about 1 hour or so because the library closes at 5. So let's get started. This is chapter 12, Generative Deep Learning, and it covers text generation, deep dream, neural style transfer, variational autoencoders, and generative adversarial networks. The potential of AI to emulate human thought process goes beyond passive tasks such as object recognition and reactive tasks such as driving a car. It extends well into creative activities. When I first made the claim that in a not so distant future, most of the cultural content that we consume will be created with substantial help from AIs, I was met with utter disbelief. Fast forward a few years ago, in summer of 2015, we were entertained by Google's Deep Dream algorithm, turning an image into a psychedelic mess of dog eyes and pareidolia artifacts. In 2016, we started using smartphone application to turn photos into paintings of various styles. There was a movie called Sunspring, which also came, and it was generated using a script written by a LSTM. LSTMs are networks which can like remember long-term information, and they are a major network over RNNs. Maybe you have recently listened to music that was tentatively generated by neural network. So it has definitely brought so much changes in terms for artists and new people who are getting into art, and it is exploding their creativity. However, it cannot like replace human screenwriters, painters. AI isn't about replacing our own intelligence with something else. It is about bringing our lives and work more intelligence of a different kind. AI will be used by humans as a tool to augment their own capabilities, more augmented intelligence than artificial intelligence. A large part of artistic creation consists of simple pattern recognition and technical skill. That's where AI comes in. Machine learning models can learn the statistical latent space of image, music, stories, and they can pick a sample from this space and create new art and work with characteristics similar to those the model has seen before in its training data. Sampling is hard, It is a mathematical operation, and in the hands of a skilled artist, algorithm generation can become meaningful. I think computers cannot do it, but a human can easily interpret if it's a good or a bad version, combining other informations as well. What's more, it can make artistic creation more accessible by eliminating the need for technical skills. In this chapter, we will explore various angles and the potential of deep learning to augment artistic creation. We'll review the sequence data generation, deep dream, and image generation, both using variational autoencoder and generative adversarial network. Let's get started. Text generation. In this section, we'll explore how RNNs can be used to generate sequence data. We'll use a text generation as an example, but the exact same techniques can be generalized to any kind of sequence data. Sequence data is no way limited to artistic content generation. It has been successfully applied to speech synthesis and to dialogue generation for chatbots. The Smart Reply feature by Google is an example of that. You can also generate musical notes and more time series data from it. Now let's talk about a brief history of generative deep learning for sequence generation. In late 2014, few people had seen LSTM even in the machine learning community. Successful applications began in 2016 with LSTM algorithm in 1977. In 2002, Douglas Eck at Scandinavia Lab in Switzerland applied LSTM to music generation for the first time with promising results. Eric is now a researcher at Google Brain, and he started a new research group there called Magenta, focusing on applying modern deep learning techniques to produce engaging music. Sometimes good ideas take 15 years to get started. That's a powerful reminder that you do not need to rush into the process to learn a new concept or a new subject. It might take a long time to just build something new. In late 20,000, Alex Graves used RNNs for sequence data generation by applying recurrent mixture density network to generate human-like handwriting using time series of pen positions. So this is also related to art. And between 2015 and 2017, RNNs were used for text and dialogue generation, music generation, and speech synthesis. The best known in 2017-18, we had language modeling. The best known example is GPT-3 that we use so much. It is a 175 billion parameter text generation model trained by startup OpenAI on large corpus, including most dignity available books, Wikipedia, and a large fraction crawl of entire internet. GPT-3 made headlines in 2020. So the question is, how do you even generate sequential data? The universal way to generate sequence data is to train a model. Like every training process has seen and unseen data, so model learns features from the training data and learns the features from it, and then you test your model's performance on the testing data, which is totally unseen to it. There is usually 80-20 test split, and we then test the performance by testing it on unseen data. And here the sequence data is usually time series data dependent on time, and you use the existing time series data to predict the next token, next word, next sentence, or something like that in sequence data. For instance, given the input, the cat is on the The model is trained to predict the target mat, the next word. So we train it with the existing word sentence and the next word. As usual, when working with text data, tokens. So each word is called token. Tokens are typically words for characters, and any network that can model the probability of the next token given on the previous ones is called language model. So this is the definition of language model. A language model captures latent space of language and statistical nature. Once you have trained a language model, you can sample it, generate new sequences, you feed it an initial text of string, ask it to generate next character or next word. Once the model has learned how to work on language model and predict the next word, now you can feed a new sequence this with its initial text of string, and it can generate a new character or new word for you and then output it to you, and you can repeat the process many times. For example, look in this figure. The initial text is the cat sat on the. It is being fed into the language model. There is probability distribution over next word and a sampling strategy, and then it predicts mat. So next is the cat sat on the mat, and then the same process happens and it predicts the new word. This is the process of word by word text generation using language model. Now you may ask, what is the importance of sampling strategy? When generating text, the way you choose the next token is very important. A naive approach is greedy sampling, consisting of always choosing the most likely text in the next character. But such an approach results in repetitive, predictable strings that don't look like coherent language. More interesting approach makes slightly more surprising choices. It introduces randomness in the sampling process by sampling from the probability distribution for the next character. This is called stochastic sampling, also called stochasticity or randomness in the field. In such a setup, if a word has a probability of zero point 0.3 being in the next sentence according to the model, you will choose it 30% of the time. Note that greedy sampling can also be cast as sampling from probability distribution, one where certain word has probability either 1 or 0. Sampling probabilities from the softmax output of the model is neat. It allows even unlikely words to be sampled, some of the time generating more interesting looking sentences and sometimes showing creativity, coming up with new realistic sounding sentences. But there is one issue with this strategy. It does not offer a way to control the amount of randomness. So sampling probability doesn't allow to control the amount of randomness, whereas stochastic sampling allow you to control the randomness, and sampling can also do so. Greedy sampling gives you an output either 1 or 0. So softmax isn't like used to control the amount of randomness. So why would you want more or less randomness? Why would you want to control the amount of randomness? Consider an extreme case. Pure random sampling where you draw the next word from a uniform probability distribution. Every word is equally likely. This scheme has maximum randomness. In other words, this probability distribution has maximum entropy. Naturally, it won't produce anything interesting because the words will are equally likely and it can repeat itself. At the other extreme, greedy sampling does not produce anything interesting either. Has no randomness. Okay, so greedy sampling also has no randomness. The corresponding probability distribution has minimum entropy. Sampling from the real probability distribution that is output by model softmax function constitutes an intermediate point between these two extremes. So greedy sampling is on one extreme and random sampling is on other extreme. One is of maximum entropy and another is of minimum entropy. And sampling from real probability somewhere in the middle. And it is an intermediate point between both of these extremes. But there are many other intermediary points of higher and lower entropy that you may want to explore. Less entropy will give the generated sequence a more predictable structure, and they will be more realistic looking, whereas more entropy will give in surprising and creative sequence. When sampling from generative models, it is always good to explore different amount of randomness in the generation process, because we are humans and we are the ultimate judges of how interesting the generated data should look. In order to control the amount of stochasticity in the sampling process, we'll introduce a parameter called softmax temperature, which tells us how creative the output is, which characterizes the entropy of the probability distribution used for sampling. It characterizes how surprising or predictable the choice of next word will be. Given a temperature value, a new probability distribution is computed from the original one by reweighting in the following way. Now let's see this graph. This is reweighting a probability distribution toward different temperature. So original distribution was a 1D numpy array of probability values that must sum to 1. Temperature is a factor quantifying the entropy. So we are importing numpy as NP. We create a definition function called reweight distribution, which takes the parameter original distribution and a temperature. So distribution is log of original distribution divided by temperature, and you take the exponent of the distribution, and then you return the distribution upon sum of the distribution. So it returns a reweighted version of original distribution. The sum of distribution may no longer be 1. So you divide by its sum to obtain the new distribution. Higher temperature result in sampling distribution of higher entropy that will generate more creative data, whereas lower temperature will be less random and more predictable. You can see here is probability, here is words, and here is temperature. So with less temperature, it's like less random and more predictable, whereas here it is like not random, more creative and different outputs. Let's see how we can implement text generation with Keras. Let's put these ideas into practice in a Keras implementation. Keras is a library used a lot in deep learning. The first thing you need to do is a lot of text data. You need a lot of text data that you can use to learn a language model. You can use any sufficiently large text file or a set of text file like Wikipedia, Lord of Rings, and so on. In this example, we will keep working with IMDb movie review dataset from last chapter, and we will learn to generate never read before movie reviews. As such, our language model will be a model of style and topics, this movie review specifically rather than general model. So we will start with preparing the data first. Just like in the previous chapter, let's download and uncompress the IMDb movie review dataset. So we are using something called wget, and from this link, it is a zip file in the .gz format. We will unzip it and we'll download it. You're already familiar with the structure of data. We get a folder named ACL IMDb containing 2 subfolders, one for negative sentiment movie reviews and one for positive sentiment. There is one text file to view. We'll call it text dataset from directory. Text dataset from directory with label mode equal to none to create a dataset that reads from these files and leaves the content of each file. Now we will create a dataset from the text files. So one file will be one sample. Import TensorFlow STF. From TensorFlow, import Keras dataset. Keras utils text dataset from directory. Directory is this folder. Label mode none. Batch size is 256. Dataset equal to dataset map lambda. XTF dot strings regex replace this and this. Strip the beer HTML tag and replace it with space. We don't need this tag. Now let's use text vectorization layer to compute the vocabulary we will be working with. We'll only use the first sequence length words for each review. Our text vectorization layer will cut off anything beyond that, then vectorizing a text. Preparing a text vectorization layer. From TensorFlow Keras layers, import text vectorization. Sequence length 100, vocab size 15,000. Text vectorization is text vectorization, which inputs max tokens is vocab size of 15,000. Output mode int, output sequence length is sequence length. So we will consider the top 1500 most common words. Anything else will be treated as out of vocabulary or UNK. We want to return integer word index sequences. We will work with inputs and targets of length 100. But since we will offset the target by 1, our model will actually see sequences of length 99. Text vectorization.adapt dataset. Let's use the layer to create a language model dataset where input samples are vectorized text and corresponding targets are same text offsetted by 1. Setting up a language modeling dataset. So we create a definition, prepare LM dataset, language model dataset, which takes input text batch. We are converting a batch of text into a batch of integer sequences because computers only understand in the terms of bits, bytes. So we will just take those. Vectorized sequences is a variable created by passing text back to batch to text vectorization function. X is vectorized sequences by cutting the last word of it, and Y is also similar. And then we are returning X and Y. And we map the dataset, prepare LM dataset, and num parallel calls. We create targets by offsetting the sequences by 1. Now let's talk about transformer-based sequence-to-sequence model. We'll train model to predict a probability distribution of a next word in a sentence given the number of initial words. When the model is trained, we will feed it with a prompt. Sample the next word and add that word back to the prompt. We will feed it with a prompt, sample the next word and add that word back to the prompt and repeat it until we have generated a short paragraph. Like we did for temperature forecasting in chapter 10, we could train a model that takes as input sequence of n words, simply predicts word n plus 1. However, there are several issues with this setup. First, the model will only learn to produce prediction when n words were available, but it would be useful to able to start predicting with fewer than n words. Otherwise, we'd be constrained to only use relatively long prompts. We didn't have this need in chapter 10. Second, many of our training sequences will mostly be overlapping. Consider n equal to 4. The text, a complete sentence must have minimum 3 strings. A subject, a verb, and an object would be used to generate the following training sequence. A complete sentence must have, sentence must have at, and so on until verb and object. A model that treats each sequence as an independent sample would have to do a lot of repetitive work, re-encoding multiple times subsequences that it has largely seen before. In chapter 10, this wasn't much of a problem because we did not have many training samples in the first place and we needed to benchmark dense and convolutional model for which redoing the work is the only option. We can remove this problem by using strides to sample our sequences, skipping a few words between two samples, but that would reduce our number of training samples. To address these two issues, we will use a sequence to sequence models. We will feed sequence of n words into our models and we'll predict the sequence offset by 1. We'll use casual masking to make sure that for any I, the model will be only using words from 0 to I in order to predict the next word. This means that we are simultaneously training the model to solve n most overlapping but different problems, predicting the next word given a sequence of from 1 to n prior words. At generation time, even if you only prompt the model with single word, it will be able to give you a probability distribution of the next possible words. For example, in earlier case, next word prediction that sat on the mat is the word which is being predicted. But in sequence to sequence modeling, it can predict upcoming words. The cat sat on the mat, the cat sat on the mat, and things like that with multiple versions on it. Sequence to sequence modeling simultaneously optimizes for multiple prediction problem. Note that we could have used similar sequence to sequence setup on our temperature forecasting problem. Given a sequence of 120 hourly data points, learn to generate a sequence of 120 temperature offset by 24 hours in the future. You'd be not only working on the initial problems but also solving the 190 related problems of forecasting in 24 hours. Just gonna check. Hmm. Given I runs from 1 to 20 prior hourly points, if you try to retrain RNNs from chapter 10 and a sequence to sequence setup, you'll find that you get similar but incrementally worse results because constant of solving this additional 119 problems with the same model inter- interferes slightly with the task we care about. In the previous chapter, we learned how we can use for sequence to sequence learning in the general case, feed the source sequence into an encoder and then feed both the encoded sequence and the target sequence into a decoder that tries to predict the same target sequence offset by one step. When you're doing text generation, there is no source sequence. This is such an important difference that when we are doing text generation, there is no source sequence. We are just trying to predict the next token, the target sequence given past tokens, which we can do only using decoder. And thanks to casual padding, the decoder will only look at 0 to 1, 0 to n to predict the word n plus 1. Let's implement the model. We are going to use the building blocks in chapter 11 for positional embedding and transformer decoder. A simple transformer based LM from TensorFlow Keras import layers embeddings dimension 256, latent dimension 2048, number of heads 2. Softmax over possible vocabulary words computed for each output sequence timestamp. So first we define input as keras.input, shape is none, D type is N64. Then we use a layer called positional embedding, which takes input sequence length, vocab size, and embed dimensions. Let's go and see what was our sequence length and size was. So sequence length was 100 and vocab size was 15,000. So this will be 100, 15,000, 256 and then inputs. This is then passed through a transformer decoder layer, which is dimension, latent dimension, number of bits, and this input to input itself. So the output will be an output from dense layer with vocab size and softmax activation, which will give us the probability of getting that input. The model will be input and output mapping together. Here, we don't have train test split because all the input is fed as input and output at once, and then we use a compile layer to with sparse categorical cross entropy and optimizer RMS prompt. A text generation callback with variable temperature sampling. We'll use a callback to generate text using a range of different temperatures after every epoch. This allows you to see how generated text evolves as model begins to converge, as well as impact of temperature in sampling strategy. We'll use the prompt this movie. All of a generated text start with this text generation callback. Import numpy as np tokens index. There is a dictionary. Enumerate text vectorization. Get vocabulary. Dictionary that maps word indices back to strings or can be used for text decoding. We make a function called sample next, which takes predictions and has temperature 1. uh, we convert it into array and float type float 64. We take a log of prediction upon temperature to see how creative it is. Then we take an exponent of it, and then we take exponent of predictions and divide it by its sum. And then the probability is a random multinomial from 1 to 1, and then we do our max of all the probability. We also have a class text generator and a callback. If this is the initial function, we take self prompt, we generate length, we model input length, the temperature, range of temperature used for sampling. How many words to generate is given by generate length. This is our prompt. Self.prompt self.generate length, self.model input length is equal to model input length, self.temperature is temperature, self.print frequency is print frequency. Definition: on epoch end, self epoch logs none. If epoch plus 1 divide mod self print frequency is not equal to 0, return. When we generate text, we start from our prompt. For temperature in self temperature, print generating with temperature sentence self prompt. For I in range, self generate length, tokenize sentence, text vectorization sentence. So we start from our prompt sentence, we feed the current sequence into our model, we retrieve the prediction for the last time step and use them to sample an input. Prediction self model tokenize sentence next token equal to sample next prediction 0 to 1 sample token index next token sentence sample token print sentence. We will run an example of this and we'll see how what the output will be. Prompt is this movie. Next gen callback text generator. Prompt generate text length, model input length, sequence length, and these are varying temperature. Sample text. Let's fit this thing. Fitting the language model. Model.fit LM dataset 200 epochs callback text gen callbacks. Here are some cherry-picked examples of what we are able to generate after 200 epochs of trainings. Note that punctuation isn't part of the vocabulary. With temperature equal to 0.2. This movie is unknown of the original movie, and the first hour of the movie is pretty good. But it is a very good movie. It is a good movie for the time period. This movie is unknown of the movie. It is a movie so bad that it makes you laugh and cry at the same time. It is not a movie I think this is a rubbish output, like it doesn't make much sense. So let's see what temperature 2.5 gives us. It is like more creative. This movie is one of the best genre movie of all time. It is not a good movie. It is the only good thing about this movie, I've seen it for the first time and I still remember it being a dash movie I saw in a lot of years. This movie is a waste of time and money, complete waste of time. I was surprised to see that movie was made up of good movie. So it's also like extremely negative as we can see. With temperature zero point 0.7, this movie is fun to watch and it is really funny to watch. All the characters are extremely hilarious. Also, the cat is a bit like Dash Dash and hat. The rules of movie can be told in another. See, here you can see it has like multiple different words that are being generated into this output, and definitely is creative and has like more output words in it. With temperature one, this movie was entertaining. I felt the plotline was loud and touching, but on the whole, a sharp contrast to the artistic of original. We watched the original version, however, whereas something something, yeah, I think it is okay. This movie was possibly the worst film about 80 women is as weird like Barker movie, but in general, great buddies. So yes, no decorated shield, even land dinosaur, Ralph and um, okay, got it. So as you can see, a low temperature value results in a very boring and repetitive text, and sometimes can cause the generation process to stuck in a loop. With higher temperature, the generated text becomes more interesting. Surprising. Oh, my library is about to close, so I might have to like wrap up this video in about 5 minutes. So let's get going. The generated text. With higher temperatures, the generated text becomes more interesting, surprising, and even creative. With the high temperature, local structure starts to break down and output looks largely random. Here, a good generation temperature would seem to be about zero point 0.7. And it's good to always experiment with multiple sampling strategies. Note that by training a bigger model, run more data, you can achieve generated samples that look far more coherent and realistic than this one. But with a deep stack of transformer decoders and much big training corpus, don't expect to generate any meaningful text other than random chance and the magic of own interpretation. Natural language is a many thing, a communication channel, a way to act on the world, a social lubricant, a way to formulate, store, and retrieve your own thoughts. The deep learning language model, despite its name, capturely affects none of the fundamental aspects of language. It cannot communicate, it cannot act on the world, it cannot be social, it does not have any thoughts to process with the help of words. Language is the operating system of the mind. And so, for language to be meaningful, it needs a mind to leverage it. What if our languages did a better job of compressing communications, much like how computers do with most digital communication? Language would no less meaningful and still fulfill its purpose, but it would lack any statistical structure. Wrapping up this topic, we can generate discrete data sequence by training model to predict the next tokens given previous tokens. In case of text, such a model is called language model, can based on either word or characters. Sampling the next token requires a balance between adhering to word model changes like introducing randomness. One way to handle this is notion of softmax temperature and always experiment with different temperatures to find the right ones. So till now we read about pattern recognition, sampling, text generation, how RNNs were used earlier, and how people use musical notes to generate new music. We read about history of DL for sequence generation and how GPT-3 was born at a startup called OpenAI and it was a text generation model. How we generated sequence data from RNN, LSTM, how we used previous tokens to generate next token as output, and it was all happening in latent space of language. We had a probability distribution over next word. Initial text fed into a language model. This went to probability distribution of next word, and a sampling strategy gave us the sampled next word. But what is the importance of sampling strategy? There is greedy sampling that uses the most likely character, repetitive, it is repetitive. Then there is stochastic sampling, it gives the probability and but also includes randomness. It gives us output between 1 or 0 of a certain word. Sampling probabilistically uses softmax layer and uses randomness to give the output. So this is somewhere in the middle of minimum and maximum entropy, and this temperature value is used to enhance the creativity and include randomness in our output. For example, this figure. Then we learned how to implement a text in Keras. We downloaded the IMDb movie dataset. We created a dataset from text files. We prepared a text vectorization layer that took sequence length, vocab size, and max tokens. We set up a language modeling dataset. We learned about a transformer based sequence to sequence modeling. We learned to interpret the outputs and how it performs. We generated a text generation callback with variable temperature sample next, and we generated a class called text generator, which took in a prompt and generated with varying temperature the outputs. So this was the output with different temperatures, and we found out that the output of 0.7 was the most optimal one. And a low temperature value results in very boring and repetitive text. The high temperature value, it looks random, but somewhere in the middle is a good generation temperature that is a balance between multiple sampling strategies. So that's how we read about text generation using a language model. Next topic will be deep learning, which we will cover in our next lecture. I hope you guys enjoyed this, and stop my stream. Thank you guys for joining me for this lecture, and I hope you guys have fun. I tried to live stream everything, and although it might be messy, but I really enjoyed learning about this topic. I try to code it in Python, and maybe in the evening or in the upcoming days, I might record a video of that as well. So stay tuned. Thank you for following me. Follow the channel Shruti Mandaokar for more. Thank you.